Okay, this is section 2.7, part 2. It's going to be all about function composition. Do a bunch of examples using composition and kind of explain what it is. And then I'll probably do like one example that's an applied, like an application where composition actually occurs. So composition of functions is when we take a function and plug it in where the x is on another function. So if we have two functions, f of x and g of x, the composition f, and it gets like an open circle, f of g of x, is the same meaning as saying whatever f of x is, plug in g of x for its variable, for its input. If we think back to the beginning of the chapter, first talking about the definition of a function, we used function machines to talk about examples. So for instance, let's say, using this idea of what composition is, let's say we have a function, f of x, that's the square root of x, and g of x, that is x squared plus 1. Okay? Now, the composition is saying take this entire thing, whatever g of x is, and plug it in where the x belongs on the other function. Okay? Using the machine diagrams, right? They draw, usually in the book, they have like boxes, and then they show I'll start with an x, and I plug it into the machine that represents g of x. This is for composition f of g of x, or f of g of x. Usually we use the composition symbol, that little open circle, but it can be written with the parentheses as well. So to do this, I'm going to take whatever value x is and plug it into the g function first, and then that output, that number I get out, is going to be, well, it'll be whatever x squared plus 1 is, but I'm going to take that value and then plug that into the other function, f of x. And I'll arrive at the square root of x squared plus 1. Right? This is how our functions work. I don't know if the machine diagrams in the text look this way, but basically what it's saying is if I start with an x, it's going to go into this blank space. And it comes out as x squared plus 1. But then that is going to get plugged into a second machine, and it gets into this blank space. So I take the square root of that x squared plus 1, which arrives me there. That's our machine diagrams. They also show a little bit in the book of the mapping diagram as well. Let me just get to the right page. On page 213. So there's the definition of composition. That's our composition symbol. So instead of a dot like multiplication, it gets an open circle, composition. But we have an idea of the mapping diagram. If you think of this blue as being all the possible inputs for G, you could put them into G and then get out something that's your range, right? Your G of X's. And then those numbers are becoming the input for F. And then you get your output, which is the F of G of X's. Composition does it all in one step for us. So I'm going to do a lot of the examples that are in the section in case especially that this may not be, it could be this is the first time you're seeing composition of functions, or it could be that this is something you haven't seen for a very long time. So I want to make sure I'm finding it worrisome to be teaching about this in a pre-recorded lecture. So we'll probably do some group work or some sort of something live in class, because I want to encourage questions, because composition of functions is not as natural as just like adding two functions together or something. Okay, so I'm going to work with example 3. And in example 3, they give us two functions. This is on page 213. they give us two functions. F of x is x squared, and g of x is x minus 3. And we're asked to find the composition f of g of x and g of f of x and their domains. And then we're asked to plug in some values as well. So f of g and g of f. So they asked for Fog and Goff, the f of g and g of f, using these functions. So remember that f of g of x gets plugged into f of x then, right? So g of f of x, yeah. And then for our second case, the order is swapped around. Now, using the actual functions, looking at the first case, f of g of x is going to be, take this g of x, take x minus 3, and plug it into the x squared. So we get x minus 3 squared. Gets plugged in for us. And then we could evaluate it. We could say, what is f of g of 5? Okay, plug in 5. 5 minus 3 is 2. 2 squared is 4. And then we could do our other direction, the other way we're asked. We're asked to take the f and plug it into g. So we take f, which is x squared, and we're going to plug it in to the function g. So x squared gets put where the x was in our g function. So this would be our composition in this direction with this order, and g of f of 5 would be 5 squared is 25 minus 3 is 22. So very different answers depending on the order, very different looking functions depending on the order. So the order matters that you perform your composition in. The order makes a big difference. So you want to pay attention. It's not like adding and multiplying where you can do it in any order. It's not commutative. It's not a commutative operation. Let's do a few more. We were supposed to talk about the domains as well. So domains. The domain for x minus 3 squared. Well, I can square negative, positive, zeros. I can square anything, and I can subtract from anything. So we're looking at all reals here. Likewise, x squared minus 3. I can still plug in anything and square it and then subtract. There's no like square roots or anything to really throw me off of that all real numbers. This symbol, by the way, means all real numbers. I don't know if that's something people are familiar with or not. So our domains ended up being the same, but when we looked at the two functions, they're similar looking, but they're not the same. And when we plug in the number 5, or we could have picked a different value as well, but we get very different answers out. All right, so let's take a look at something a little more going on. How about the compositions in example 4? So in example 4, f of x is the square root of x, g of x is the square root of 2 minus x. Okay, so we're going to do some compositions here. Let's say we start by saying, let's do f of g. So f of g of x is to say take g of x and plug it in on f of x. So that's f of g of x. So we can think of f of g of x, let's take f and plug in the square root of 2 minus x. And we know what the function f looks like as well. It's also a square root function, so we're going to take the square root of the square root of 2 minus x. Yuck. A little bit nicer way of writing it, when you take the square root of a square root, that's the fourth root. And how about a domain here? What sort of numbers would be okay for the domain? What numbers can be out the inputs? Well, I can't take the square root of a negative. I'm sorry, the fourth root of a negative. That's not allowed. So if 2 minus x makes a negative number, it's not okay. It's okay for it to be 0 or anything bigger. So that means my domain is any numbers as long as it's 2, because if it is equal to 2, that'd be 0, which is okay. It can be equal to 2 or bigger, or I'm sorry, or smaller numbers. I got my order backwards on what I was thinking about. So it can be equal to 2, and things smaller than 2 are going to mean that this is still a positive amount. Okay, how about if we try and compute, let's say, g of f of x. That's take g and plug in f of x. Okay, well, g says, or sorry, f says square root of x. So anywhere for g that there's an x, you plug in square root of x. Okay, I could do that. That says then that we have the square root of 2 minus the square root of x rather than just x. Now, what is going to be the domain here? Well, when I choose a number for x, it's got to be at least 0 or bigger. Otherwise, this first little square root is going to get all messed up. We won't be able to do it. So we already know that x has to be bigger than or equal to 0. And then we have to have that 2 minus the square root of x has to be bigger than or equal to 0, because that 2 minus the square root of x is also underneath the square root. It's also under a radical. And so that's going to happen when x is less than 4, right? Because if we plug in 4 for x, just for a moment, I'll plug it in here. If we were to plug in 4, we'd have the square root of 4 is 2. And that'd be 2 minus 2 is 0. Square root of 0 is okay. But if this was something bigger than 4, let's say we plugged in 9. 9, 2 minus the square root of 9, that's 3, which makes it a -1, which is not okay. So we're allowed to use numbers equal to 4 or less than 4 for x. So we're going to see anything less than or up to 4. But don't forget, also can't have negative numbers plugged in, right? Because you can't take the square root of x and have it be a negative that you plug it in. So we actually don't include all the numbers. It's a much smaller interval. We're allowed to use 0, and we're allowed to use 4, and it's all the numbers in between 0 and 4. So that one was a little bit more complicated just because of the double square root that we couldn't get rid of. Okay, how about same two functions, but we're going to do more compositions, different compositions. So I'll just remind f of x square root of x and g of x is square root of 2 minus x. So let's say we want to take the composition of f with itself. That's possible. It means take f of x and plug f of x into it. Okay, so we're going to take f of the square root of x. So wherever x was, make it the square root of x. So that's, well, the square root of the square root of x, or the fourth root of x. And what would our domain look like? Well, the fourth root of x, I can plug in 0 and anything positive. And last one, what's g of x? G composed with g. Well, that's g of x. So take g of x, square root of 2 minus x, and plug it into g of x. So take that, and we have the square root of 2 minus the square root of 2 minus x. Yuck. It's not pretty. But we can figure out the domain. We can. So looking at where the x is, this expression is going to be defined whenever 2 minus x is not negative, right? Because of this first square root here, the smaller one. But also, the 2 minus the square root of 2 minus x has to be not negative. When both of those things are true, we'll be in the domain. So the first case, 2 minus x is bigger than or equal to 0, tells us that that means that x is bigger than, no, sorry, x is smaller than or equal to 2, right? You could add x on both sides, and you'd be right there. This second piece, however, is equivalent to saying, I think I deserve a little more writing space. Oh, I don't like when it does that. Okay. That's equivalent to saying the square root of 2 minus x, or here, I'll write it in a way that's clearer. Add the square root of 2 minus x on both sides, right? So we're just adding this thing on both sides. So our inequality says 2 is bigger than or equal to the square root of 2 minus x. And I can continue to solve this inequality. I can square both sides. I get that 4 must be bigger than or equal to 2 minus x. And then we can solve this inequality, and it tells us that, right, you could add x to both sides if you want to do it that way, or subtract 2 on both sides, which will say 2 is bigger than or equal to negative x, multiply by negative 1 on both sides, which means we flip the sign around. It means x is bigger than or equal to negative 2. So we need to have x be bigger than or equal to negative 2 while still being smaller than or equal to positive 2. So our domain is from negative 2 to positive 2, because that's what's going to hold both of these inequalities true. One inequality from each of the square roots operations that's happening. So in this example, this was a big example, but in this example, we looked at taking the composition of f and g in one direction and then in the other direction, right? F of g and g of f. And then we also looked at taking f of f, f composed with itself and g composed with itself. You can take the composition of more than 2 functions. You can take the composition of an infinite amount of functions. So for instance, if you're given 3 functions, let's say you're told f of x equals, I'm going to use example 5 on page 214. So f of x equals x over x plus 1. g of x is x to the 10th, and h of x is x plus 3. So you can compose things with more than two factors, composition factors, I suppose is what they'd be called. So f of g of h of x. And we're going to read it from right to left. And so we're going to, if you want to use just parentheses without the composition symbols, whatever you get from h of x, that's going to get plugged into g, and then that amount is going to get plugged into f. So we can compose this and try and make it nice and pretty and simplified in the end, hopefully, but we'll get it as nice as we can. We're not going to go above and beyond today. But when we plug it in, so let's take h of x and plug it into g of x first. We start from the innermost, or we start from the right. So we're going to take x plus 3 and plug it in to g of x. So that's going to say f of x plus 3 to the 10th. That's h of x is x plus 3. It's plugged into the place where the input belongs on g. Now this expression, x plus 3 to the 10th, is going to get put into the fraction, the rational function that is f. So we have in the numerator x plus 3 to the 10th over x plus 3 to the 10th plus 1. This would be our full composition. We've combined all the way through. So as you practice this skill, I think it'll get a little bit easier, a little more natural to you. But if this is something that's new or really out of practice, compositions of functions may take a few exercises till you're really getting used to it and getting back into it. The last thing I want to talk about in this video is an application for composition of functions. So there's a bunch of application problems actually at the end of this section in the exercises, and some of them will be in the assigned homework. But I'm going to do example 7, an application here where they're talking about ships that are traveling and talking about the distance between an ocean, a ship out in the ocean based on the time of day and its reflection and the lighthouse and all this stuff. So if we look at example 7 on page 215, we have a nice word problem. The ship is traveling at 20 miles per hour parallel to a straight shoreline. It's nice that they gave us a picture, but just in case there wasn't a picture, let's think about having sand. This is the shoreline, and this side's water, and here is the ship. And it's traveling parallel, so it's traveling in the same direction of the shore. And we're told it's 20 miles an hour that it's traveling. I didn't know they measured in miles per hour. And the ship is 5 miles from the shore. It passes a lighthouse at noon. So there must be, I always think of the striped lighthouses, so mine's going to be striped. There must be this ugly lighthouse, because I can't draw worth to save my life. But the distance from the ship to the shore, we're told, is 5 miles. That also means the distance from the lighthouse to the ship's path will be 5 miles because it's running parallel. That distance won't change. And it passes the lighthouse at noon. So at noon, perhaps my lighthouse should be down here based on what the question's about to ask me. So at noon, the ship is here. Later than noon, it's moved. And we're asked to express the distance s between the lighthouse and the ship as a function of d, the distance the ship has traveled since noon. So they're defining our variables for us. S is distance to lighthouse. I hate using S's because they look like 5s. D is distance from, let's say noon or 12 p.m. ship position. So if the ship knows how far it traveled, we're going to make a function so that you can then calculate how far from the lighthouse it is. Okay, and then parts B and C, we're asked to express this function as a function of time. Yeah, we'll get to part B. Let's start with part A. This is part A. So we want to relate the distances, and we can do so by observing the Pythagorean theorem. So do you guys see the triangle? Maybe not. But later when the ship is up yonder, ooh, not meaning an eraser, but when the ship is up yonder, it is a distance from the lighthouse. The distance from the lighthouse we're representing with an S. The distance the ship traveled would be a D. So I'm just going to draw that same triangle out of my big picture so that I'm not drawing on top of myself too much. So this is the lighthouse. This is the ship now at p.m., like 2 p.m. or whatever, later, afternoon. That's what I want to say, afternoon. And this is the 12 p.m. ship, the distance, the spot that it was at noon. So because we end up with this right triangle, we know it's a right angle because this side and that side were on parallel. This would be then a transversal, if that's a language that you speak. And that the distance between the ship now and the lighthouse is called S. The distance from the ship's position at noon and where it is now we call D. And the distance between the lighthouse and the ship we know is 5 miles. So by Pythagorean theorem, I can set up that S squared equals D squared plus 5 squared. And I want to make it just say S though, because I'm asked to create a function that expresses the distance S as a function of D. That means solve it in terms of D. Solve for S in terms of D. So we take the square root on both sides, and we get that S equals D squared plus 25 underneath the square root. If we're going to use function notation, as they did ask us to, they want it to be f of d. So our function for part A, and I'll be able to come back to my picture, but our function for part A would say f of d equals the square root of d squared plus 25. Okay, that's where that function's coming from. In part B, the second part of the problem, they ask us to express d as a function of t, to express the distance between the ship's position now and its position before as a function of time, where t is the time that elapsed since noon. So part B is actually a simpler function to find because we know the ship is going 20 miles per hour. So every hour, it'll be another 20 miles, meaning that the distance will equal the speed, 20 miles per hour, times the time. They did ask us, though, to not call it d equals, to do it in function notation. So I can rewrite that instead of with d. They ask us to call it g of t. And that's written in the instructions for the problem. But the distance equals the speed times the time. And then in the last part, we're asked to compose these two in a way so that it will say F composed with G of T. So what we're going to do is we're going to take G of T, we're going to take that expression and plug it in where the input goes on the other function. So we have the square root of 20t, and I'll write that in parentheses, squared plus 25. And this equation, what does it represent? Well, we're taking the distance. Remember this G of T represented the distance. This is D, basically. G of T was another way of writing D. So we're going to take the distance based on time. We'll be able to calculate the distance the ship traveled. And then using that distance that it traveled, we can then calculate the distance from the lighthouse. So it allows us in one step to take an input, which is T, time, probably measured in hours, and get an output that represents S, our distance from lighthouse. So this is just one example of how compositions get used when we see, especially when we see more complicated formulas out in real life, especially, you know, like physics formulas, stuff like that, like how different things work. It's usually a composition of some simpler formulas. It's just that they happen to all interact with each other, and so they can be included in one formula that can take care of everything at once instead of breaking it up into 100 smaller pieces. All right, so I will post the videos for section 2.8 as well, because that is connected with this section in our setup for the course. And there will be homework posted for these sections as well.